So hi everyone. I'm Leslie Kanthan, and thanks for the introduction. And it's a pleasure to be here to discuss with you what it is that we do, and in particular how this use case applies for signal processing and communications in general. So I want to give a bit of story background about ourselves. So we all have backgrounds in machine learning, specializing in different areas of distinct areas of research to do with that. I have a background in history within financial markets, automated market making, quantitative trading, and it's during that time we saw the advent of AI being involved in model building, and we started to see how that could be applied in a more generic way. That led to us working, and myself and the original and the co-founders of TurinTech working on code optimization. So we used our machine learning techniques to essentially identify inefficiencies within code and optimize that. And as a result of that, we ended up publishing a very well-known paper now. And from the back of that, we started to build out our IP. And this is the IP that I guess everybody's talking about at the moment in the market, that people are talking about generative AI, people are talking about optimization, people are talking about how machine learning can help them in general and improve some of the processes that they have. So what we see in general is that machine learning, from what we know in the marketplace, is allowing users to get better insights from the data. And this is different from various different conventional approaches. For markets, it used to be primarily stochastic control theory based approaches. And then for outside of the financial markets in other areas and retail, mainly more different types of statistical approaches and a lot of manual process being involved. So I guess for what we're discussing here is how machine learning models are being used, in particular, analyzing the large amounts of data and getting some meaning from this data, because this data could be very unstructured, consist of texts and images. And in addition as well, about the predictive capability of these actual models. How does one get to improve the accuracy? How do they get to ensure that the models are not overfitting? And also, how do we ensure that the models are actually very efficient and give you much more insights than what the traditional or conventional approaches can be? And this is entirely automated way of thinking of solving a particular problem. And as a company, we had looked at this, and we realized that we could apply our code optimization techniques to machine learning model building and machine learning model optimization. So optimizing the actual model process at the underlying code level. So I guess you've seen that for machine learning being applied in signal processing, we have many different applications of this. And in particular, we know that data collected in this area can be quite full of noise due to many different factors. Amongst all, there could be human errors, there could be other variable sources, and there could be also environmental factors that affect the collection of this data and therefore become more noisy. So obviously there's conventional approaches that are used that you're well aware of identifying and removing such noise from the data, but machine learning algorithms are taking more and more precedence because of their ability to extract meaningful information from this data and to filter out the noise and give you a much more clearer defined data. And a lot of these techniques that are being used they involve autoencoders, they involve neural networks and various other denoising techniques, but ultimately the goal is to give you a very accurate result. We also see machine learning in converting speech and image data into signals, and then that could then further be analyzed much better. Speech data can be converted to spectrogram or mel frequency, and this can be more easily processed by your own DSP signal processing algorithms. And in the same way, image data can also be converted to more on the frequency domain representation using Fourier transform or wavelet transform, making it much easier to extract features and patterns. And machine learning algorithms in general, what we see is that the use of this for large amounts of signal data quickly and more efficiently. You can see like one example that we think of is that there are various different machine learning techniques that are involved in clustering and classification. So in particular, clustering different groups of signals, and there are techniques out there like correlation clustering that you don't need to specify the number of clusters, it will automatically cluster them. And there's other techniques that require a variable to define the number of clusters that you want to cluster, and then you can discern patterns and anomalies very easily and give meaning to them. And then in the same way as mentioned earlier, classification algorithms can be used to categorize those signals into various different classes based on more of the features that underpin them, making it much more easier to identify and ascertain what those signal types are. But in general, the problem that we see with this, I mean, it's not a problem, but there's a difficulty, is that there's a computational cost involved. First of all, and not just a computational cost, but I guess a more laborious cost as well that goes with it. Because first of all, you have the financial burden of developing and deploying machine learning models. And the reason why is mostly the technical skill that's required, the collection of researchers working on a particular type of model, then actually training and deploying this model involves the inference, the computational costs involved with all of that. And especially with cloud costs going up, those costs can exponentially rise as well. And then of course you have the time. So we have seen in some cases with some of our clients in this area that getting in from the idea concept to proof to actual deployment of the model can take anything over 18 months. And as mentioned before, look, you have mathematicians in abundant supply, you have physicists, you have electrical engineers, but actually out of them, those that have experience and knowledge in AI and distinct areas of artificial intelligence, whether that may be machine learning based approaches, supervised learning, semi-supervised learning, unsupervised learning approaches, deep learning, these kind of novel techniques is not known to all, and it's very, very difficult in essence to actually master and get something incredibly meaningful from this. So this makes it harder to hire, and also retaining that type of talent, because as the demand is high and the supply is very low, it makes it easier for other big, large technology companies to take these kind of individuals first before yourselves can basically use to utilize them correctly. Just want to check something. Yeah, that's right. Okay. So the research decisions typically in doing this kind of model optimization often involves optimizing multiple objectives or criteria, which in essence can conflict with one another. And what we mean by this, I guess, is if you think of, let's say, you think of a trading strategy and you want it to be highly profitable, but you want it to cost as little as possible to actually build and generate that strategy. So computational cost low, and the actual accuracy of the model high. The problem with that as you can obviously see right now, is that there's a computational cost involved naturally to get to the global optimal for what your model may want to be. And that means that you will have to compromise, one of those functions or features. And in essence, what you're looking at, what you're looking at is multi-objective optimization aims to look and find you the best solution given the constraints, considering that this would be on a Pareto frontier curve where you will potentially have non-dominating solutions. And using this kind of optimization techniques, researchers can make better decisions on the wide range of factors and trade-offs, and see how this can make their results more efficient. So this brings us to our platform. So we designed the product, and it is used for various different use cases, including signal processing. And its idea is to basically give you the benefits with little or no burden. And we call this product EvoML. So it's a model code optimizer, and it's used to build and deploy machine learning models for your signal processing tasks. And essentially it works as follows. First, you have to upload a data set. So you have a platform, it will do the pre-processing of the data set, look and determine statistically any identifiable variable features between those different variables and those different columns in the data, and try to see if there's anything specific or any pattern about them. You can view this, you can visualize this, and also you can basically customize that part as well. Then you will look and see how to essentially generate a trial. So a trial is considered like generating and evaluating a machine learning model, and creating the trial itself is a very simple process. It's basically a click, though again, it can be very customized as well. So you can intervene in any of the process, edit the model, choose the model that you're changing, and you can do many different things with that. And also, it's optimizing the models at the code level. So automatically, the product is designed to scan inefficiencies within the code, and this is at data structure level. So this then generates new code. That this code is optimized, and it's specifically customized for running faster given your hardware requirements as well. So it can maximally efficiently use the hardware that you have, or if you're not on-prem and you're using cloud, then it can use this for cloud too. Yeah. So I guess one thing I can mention is a potential research problem that you have analyze a computer simulation of high-speed optical communication system. And there's a data set derived that you have the simulation of the optical communication problem. And traditionally, the simulation results are evaluated by calculating the bit error ratio. Using our product, we were able to show very good accuracy and recall scores that were significantly better. And I guess the question again is, what is significant to the user? This is one of the case study results that we have when using the platform and product. What I also wanted to go into a bit more detail about is as well, like the actual research that underpins the product is very collaborative. We have worked with a number of other research institutions, some of whom are also in this meeting, to basically encourage our own research team into thinking into new ideas and developing this into a much more advanced novel IP-based product. And we have clients that range from hedge funds to banks to insurance companies to financial database companies, and even inside of the non-financial field, in also in defense, and also, as you can see from the signal processing example as well. So our product is designed to evolve and learn. It implements active learning as well. So as we train and build new models as well, and new data sets are coming in, the product is constantly evolving those models and using our optimization techniques to do that. Yeah, I guess that was a quick intro of ourselves and our product, and happy to discuss if you have any further questions.
Wonderful. Thank you so much, Leslie. Very interesting. So we'll have a few questions now. By the way, Leslie, how much time do you have? We'll just see.
I try to do it so that I have time to answer any questions that anyone may have.
Perfect. Okay, that sounds good. Thank you. So, Bo, do you want to go ahead and ask a few questions?
Okay, thank you very much, Leslie, for introducing what you do in the TurinTech. So actually, I see that like one of the major things you do in the company is to optimize the code, and yeah, I probably have some question is a little bit to go into the detail when you see optimizing the code. Do you mean like you like to what kind of the measures like we are trying to see, like when we say the optimizing, so to like to check the memory or to somehow to check the structure of the neural network or something?
So sure, it's all those things. So just to go briefly into it, so what we do is we look to optimize the code in a particular way to reduce the memory consumption of the code, the CPU consumption of the code, whilst also maintaining the integrity performance of the actual code. We use our own internal benchmarks for that as well, but sometimes unit test is provided as well with the code. But in our case, as we're doing this on a model level, we're also optimizing some of those models as well at the code level, where we provide those benchmarks. We also do this as well against hardware. So for instance, we may know that this particular piece of code runs on this hardware specification. Maybe it uses a very legacy Intel processor. We know what the performance is of running that code. And then when we create variations, and I use the word variations because what I mean to say is that actually, our product produces, as I mentioned, on a Pareto frontier curve, a number of different solutions and variants of that code. So what you can think of is that you may have code that runs much faster, but consumes a little bit less memory, right? Or equally, you could have code that doesn't run as fast, but it consumes a lot less memory. So in that instance, for instance, maybe you have your particular model, and maybe you want the actual memory of the code to actually be a lot less, right? So a lot less resource intensive, and you're less concerned about how fast it may run. Or likewise, you may want the code to be very, very fast, and you have, like, I wouldn't say near infinite, but you have huge computer power resourcing. You don't care so much about the consumption that it's using.
Yeah, actually, I have like some question, maybe too much. I hope that it's not your secret in your business. It's like, especially when we are talking about the machine learning, mostly now, like we talk about people just by default, they mean like neural networks. So for the complexity of the neural networks, somehow the complexity is predefined. So that means like once you have a trained model, so the structure is there, and also like they have the layers there, and also in each layers the coefficients, they have the certain defined resolution of each coefficients. So once we have a trained model here, so you mean that if is that possible in your platform? So we can still find is your code, it can still keep on like find some metrics to, or maybe some magics to reduce the complexity. For example, if they can identify some layers is not actually take effects of the final result. So during the, or can your code just drop off these 2 layers, or have some slightly change of the structure of the trained neural network, or
Sure.
maybe for some coefficients, they may not need that high resolution of the defined data. They can change from double to probably integers,
Yes.
or this type of like optimization.
Sure. So in those, we have an advanced version of that where we do some of what you have mentioned that is very, I guess, IP sensitive for us. But what I can tell you is that, look, so you have some model, as you mentioned, right?
Yeah.
And you have a structure for that model. But maybe there's a different type of model that you weren't thinking about that can actually be substituted and work just as well and become more efficient. Probably that would be utilized better. Then of course, what you have just mentioned about the layers of the actual model, right? The neural. So there is some complexity optimization that we do there to make that reduction, right? And then there's other various techniques that probably we can talk about much later on, because I have another meeting to go to shortly. But I just wanted to try and answer some questions on that.
Okay. Yeah, I think maybe like there is at last there is like the roundtable discussion, so maybe we can have some.
I think we can do that, because also you have to remember a number of those models that you described as well. They will have their own parameters, right?
Yes.
And tuning those parameters, optimization of those parameters for a given set, and for having a particular type of result is very important, and learning from that and being able to evolve that, because as you know, like computing the correct parameter that you may need it's an exhaustible problem in itself, right? Can be intractable in some cases. So there's very machine learning techniques that we use on top of those techniques to determine and define what that model would essentially be with the correct set of parameters. May not necessarily be a global optimal solution, but a local optimal solution that is as good as the global optimal solution, given that we don't know what the global optimal solution may be. So I just thought I would highlight that, but yeah.
Okay, yeah, great. Thank you very much.
Thank you both for your questions.
Okay, no problem.
Thank you very much, Leslie, for your talk. Very interesting. Appreciate your time today.
Okay, and I'll be back for the roundtable, and yeah.